In your project, I've had you graph the equation y equals sine of x on a couple of different grids, where each grid had a different notion of how many degrees were in a single square. And I want to talk about that, but first I want to show you something that you are more familiar with in algebra and geometry. All right, so I've got three parabolas here, and I took out the grids and I took out the axes, but I will tell you that one of these three shapes is the graph of y equals x squared, and the other two aren't. And I want you to guess which graph is y equals x squared, just based on the basic shape of it. All right. So if you're like me, you probably look at this blue graph and say, no, that's much too narrow to be the graph of y equals sine of x. It's wider than that, but it definitely isn't that wide. That's much wider than the normal graph. So this, ooh, yeah, that's just right. And if we put the grid back in, and if we put the axes back in, and if we put the grid back in, there we go. We can see that, yeah, this is going over 1 and up 1. It's going over 2 and up 4, just like the normal parabola y equals x squared does. All right. Now that we have that notion that we have some kind of intuitive idea of what a normal parabola looks like, let's take a look at the graph of y equals sine of x. So once again, I've got four different graphs, all expressing that sine wave function, but with different scales, different notions of how many degrees are in a single one of these squares. And so let's take a look at a couple of them. So like this brownish gray one or brownish red one over here, this is a really gentle curve. I have to go over 1, 2, 3, 4, 5, 6, 7, 8. I've got to go over about 9 squares before I go up to the top of this hill. So that's a really gentle hill to climb. Compare it with this one right here, where when I go 1 square from left to right, not only have I gone to the top of the hill, but I've come right back down to my starting level again. So that's a very different behavior of a curve. And so, in geometry, maybe we don't care too much about it, but in calculus, that's the kind of question we're going to ask ourselves a lot is what is the normal steepness of a sine wave? What should it look like? And the problem that we're encountering, as you've seen when you have drawn a couple of these graphs yourself, is that we don't really have an intuitive sense of what the proper scale is between degrees and ordinary numbers. Um, Really, measuring angles in degrees, it's the only time in a math class that you've ever run across a unit associated with numbers, haven't you? I mean, they come up all the time in a science class, or if you see a graph in a history book or something like that, you've got years and population or something like that, or you've got temperature over time. But whenever we've done math in with normal graphs where we're adding or subtracting or multiplying numbers, when we're doing exponents and logarithms, we're always starting with just ordinary numbers and we're ending with ordinary numbers. The only new wrinkle that came in is when we started measuring angles in this thing called degrees that we just arbitrarily decided there would be 360 of them in a circle. So what I'm thinking is, why don't we see if we can come across some way of doing an experiment that's going to yield us a graph that is a sine wave, but where we're measuring the x and y scales using the same unit. And so we're doing it without degrees. And if we do that, we might have this natural sense of what a natural angle measure looks like instead of this arbitrary decision to have 360 degrees in a circle. So keep going on with the inquiry. You're going to build up to doing some measuring and building a new kind of graph yourself. So keep going forward with that.